We're recording. Okay, all's good. Thanks.
All right. All right. Well, that being said, I'm going to go to my desktop here. Hopefully that everyone will be able to see this. Let's see. Is everyone? Okay. Are we good to go? That's good. Okay. What I'm going to do first is give you a little bit of an overview. I've done kind of a composite system based on some other projects we've done that had the issues we're going to describe. And one of the things that's critical on evaluation, as we covered in the last seminar in November, was preliminary due diligence to make sure all of your above ground portion of the problematic system is not the problem. So with that, we're going to make an assumption that for the most part, everything above ground, the heat pumps are correct, the sequence of operation controls are correct, we don't have conflicts with too much outside air, that sort of thing. So what we're going to make an assumption is that we have a package 2-pipe heat pump system. Typical heat pump for this exercise is a 6-ton nominal climate master unit. We have a total of 80 of these units. Peak equipment load flow would be 1,440 GPM. This would be a decoupled system. That is, we're only going to inject into the loop field, into the building loop when it needs to be tempered, which is a very efficient way to reduce your pumping costs. And the ground loop for this example is 120 holes, 500-foot depth by 25-foot spacing. And we're also assuming a TC test was done prior to the final design and fairly low antifreeze content, 15% by volume. So what are the issues? Well, for this example, and this is we have run into this on various projects where the ground loop was overheating, and in other words, the entering water temperature was too warm for the heat pumps to tolerate and still operate in the cooling mode. So we had chronic lockouts, poor interior comfort, and a high operating cost. So what we're assuming is, if we go through our due diligence, is we're not seeing any significant issues on the above ground. So our sequence of operation is assumed to be competent. Flow rates are determined to be okay. We're feeding enough water to the heat pumps. We're not seeing anything that really should be harming the operation of the system. So that makes us focus on the ground loop. So one of the first things that I usually do, I will try to replicate the simulation using GLD, where I'll rebuild the loop field parameters, and if the original loads are available, and sometimes they're not, because if something's in being contentious, unless a lawyer tells someone to give up the loads, you may not have them. But in this case, we're going to assume that we do have loads. So what we're going to do is we're going to go back to GLD here. And all we were provided with for this exercise was the monthly load summary of an 8760 hourly load profile. We were not provided the full hourly, so this could have come from eQuest or something like that, where the nominal output is strictly a monthly summary. You can, with eQuest, get the full hourly loads, but unless the operator knows how to do that, it may not be able to get them. So with that, you can see that we've got a cooling dominant load here. And if you'll look at your annual equivalent full load hours here, we're more than double that for the heating requirements. So what we did was we replicated the loop field. It was a for our purposes, it was a rectangle, 10 rows across and 12 rows down with 25-foot bore spacing. Bore length is 500 feet. They did use thermally enhanced grout, so we put in a .90 conductivity. Confirmed with the driller there was a 5 3/4 inch bit used for bore diameter, and 1 1/4 polyethylene pipe was used. Because geoclips were not used or any other appliance to force the loop out to the sides of the borehole, we're going to use the average placement here. And you can play with this, but you'll find that in most cases, yeah, it'll make some difference, but when you look at using thermally enhanced grout versus clips and all, it may not make that much of a difference in a lot of cases. So our thermal conductivity test parameters provided an undisturbed ground temperature of 62 degrees. We had a thermal conductivity of 1.47, and the TC test report gave a diffusivity of 1.09. And that's feet squared per day, conductivities in BTU per hour, per foot, per degree Fahrenheit change. So the specification also called for 15% propylene glycol just for a maintenance slug and also as a carrier for any inhibitors in the fluid. And what we're going to look at here is based on these monthly loads, or the summary of the 8760, we could select design day or monthly. In this case, since we have the monthly data, we're going to do it. We've also selected over here the Climate Master 6-ton TE30. So everything's the way it should be as far as what was installed. At 25-foot spacing as shown down here between boreholes. We're going to use a 5-year projection, and we're going to run this guy. So with that load profile and the loop field as installed at 5 years, that's projecting a temperature of 85 degrees. We really don't need the antifreeze based on this load profile because it's showing we're not getting that cold in the loop field. But again, the engineer wanted to use the propylene glycol as an inhibitor carrier as well, and it does provide protection for unforeseen. So let's take a look at the temperature projection using GLD. So this summary is predicting that we're going to have continuous heat creep. And just to note, and this is, GLD does not advocate this, but I'm going to tell you based on experience that for most situations, heat creep does not exist. I've heard stories where people have said, oh, after 8 or 9 years, my loop overheated. Well, if that's the case, typically at that point when the loop overheated, something changed on the loads to increase on the surface, whether they're bringing in more outside air or whatever. And we've actually gone in on jobs and determined that to be true. And we've also got a lot of trend data showing that the actual ground loop temperature, if everything was evaluated and designed correctly, this heat creep is a rare thing. I'm not going to say it could never happen, but in most cases, it's wrong. It's only in theory. So what we're going to do is look at this from the perspective, if the loop field is overheating and everything is okay on the surface, what could be the issue? Well, the first thing that I would assume is that maybe the loads were not correctly calculated. And in this case, after looking at the inputs on the loads and everything, we determined that to be true. But before we go on, I want to just show you what can happen just on spacing alone. If you'll notice at 5 years, we're predicting 85 degrees. I'm going to take this to 35-foot spacing, and I want you to keep this in mind as we go through the webinar. You'll notice that dropped a few degrees. If we look at this graph, it's it's also started to level off this potential heat creep. And of course, in theory, what it's doing is saying, okay, we're getting more area between the boreholes to disperse heat. So we're not compressing it as much between boreholes and having as much thermal interference. Okay, so we are a little concerned about this, the loads, and so we recalculated the loads, and based on an hourly profile, this is actually from Train Trace, and it's a .gh output, which is an actual CSV file. And if you'll notice, that goes to a full 8,760 hours. So we've already got this thing preloaded. We're going to bring it in just to see what's going on. So what that's done now, you'll notice, if you remember from the last load file, we've got a substantially greater total amount of cooling and heating per year. So we've got a lot more load on this thing. Now I'll confess, our full load hours are about the same proportionally. That's because to make this example fit, I actually proportionally reduce this actual load file. So if we've got this new load file, we also have to go back and make sure we've got the right heat pump selected. Because what the heat pump library file is going to do, it's going to allow the software to calculate the efficiencies at different entering water temperatures. This is another issue we find with some forensics, where someone will use a central plant or a heat pump that doesn't have good data, so they'll use another heat pump's performance profile, and you get a lot of errors if that equipment is not equivalent to the one you're selected. So just to kind of keep that in mind as well. So we've got the new file. What we're going to do is delink. I always do this, and then relink the load data and zone data back to our loop simulation. Now we're going to hit run again. Wow, what a difference. Since this job had overheated the first year, this is not much of a surprise. If we look at our temperature simulation projections, it's saying even in the first year, this loop should have been over 100 degrees. So that's telling us that, yeah, we may have an undersized loop here. So if we've determined that the original loads were insufficient for whatever reason, and we actually have more heat to reject to this loop field.
You want to set back to 25 feet, Terry?
Oh, good point. Thank you. Let's recalculate that. It's probably going to go up a little bit in temperature. It does. 116. And our first year is well over 100 degrees, as noted before. In fact, what you can do, of course, is just put it at 1 year and see where it should be. And it's saying 105.2 degrees. And you can take this to whatever projection you want. But the first or second year is usually where these things will end up if in perpetuity, unless something's going to change. That being said, our 5-year projection is saying we could be up to 116 degrees. It does fit with the complaints from the client in the first year, first summer, that this retail facility was overheating and heat pumps were chronically locking out. So what we've done now is we've recalculated loads. We think we've identified what the issue is. We were undersized. GLD simulation is replicating what's actually occurring, which is a good thing. At least we have direction to go. So what could be our potential solutions on this? Well, can we add more ground loop? Is it even feasible? Is the area available? Is it within the budget? And for this exercise, in a lot of commercial jobs, once a loop field's in, there's usually a parking lot or landscaping, in some cases a building on the top of it, so you're not going to put any more ground loop in. So what you typically have to do is focus on a hybrid element and putting in an auxiliary cooling device. So we're going to go play with that a little bit. But first, just to show you the impact, we're going to go back here. We had 25 foot for the 116 degrees. I'm going to take that actually to 40 foot spacing just to give you a perspective of what that could have helped with this system. That would have been, it would have dropped about 8 degrees off the peak, and on a 5-year projection, if you'll also notice that that slope for peaks would have really been leveled off quite a bit. So it's still saying first year a little bit over 105 degrees. So that does make a difference, but let's take it back to the 25 because we can't go anywhere else with this right now. So we're back up to 116 degrees after a while. We're not concerned about the heating side. We obviously have a cooling dominant load. So let's go back to our loads here, and I want you to keep in mind these values for the peaks and the total duration loads. So looks like we're going to have to look at adding in an auxiliary cooling tower of some sort or equivalent cooling device. So we can use GLD to determine that auxiliary capacity that is necessary. So we can go down here on cooling to our peaks, and I'm going to take this thing up to about 30% of the peak cooling load. There we go. I'm going to select update, which will modify this load profile. We're going to go back to that, and if you'll notice, we have really trimmed these peaks back, and they're all consistent now for the months of April through October. And it's saying for our totals, we've dropped we've converted about 2% of the total heat rejection to the auxiliary cooling device. So if we looked at a summary of this, our hybrid total BTU capacity that it's going to absorb annually or take off the loop is 118,874.4 kBTU for the total year, and that 2%, that's not very much. So what we're going to do is we're going to recalculate this now and see what it does, if it makes a big difference or not. And it did. It's still too hot, but it dropped us down to 109.7 degrees peak. And if we look at our projections on this, at least the first year would probably be a little bit cooler and would probably still function. In reality, it would probably work okay with this, although the efficiency would not be good and the operating cost would certainly not be good, because your EER would be a lot lower, and so between the heat pump low EER and the use of the auxiliary cooling device, your operating costs are still going to be up, but probably not as bad as locking out the system and losing customers when they leave the facility. So we know we're on the right track. So let's increase this now and go to 50%. Take off the peak cooling load, and we're going to update. And now we've dropped our peaks to the ground loop at 2,809 kBTU per hour as our peak load. And down here, that's saying we're taking off 13% of the total cumulative load per year we're sending to the hybrid device. So we're still getting a lot of use out of the ground loop. So let's see what that does for our entering water temperatures. better, but still not too good. We're still at 99.6 at 5 years. If we were to take that to 1 year, it would probably work, but we wouldn't have a lot of fudge factor. And if this is your job that you're trying to correct, or you've been hired as a third party, you want to be able to sleep at night. So you want a little more fudge factor, I would think, on this. So we're going to go back to 5 years. And so that's almost a 9 degrees difference. But what we're going to do down here is we're going to take this guy up to 60% now. Now that's down to 2247 as a peak load to the ground loop. But now we're almost to 24%, almost 25% per year of shaving off the total heat rejection to the ground loop annually. So let's recalculate and see where we're at. Now that's getting a little more acceptable. Now that's at 5 years. So let's go to 1 year. Now 86 degrees, that would probably work pretty well. So if you, just for a 1 year projection, we're only showing a little past 85 degrees and not for very long. So what we're going to do here, for those of you who are not convinced heat creep does not occur, we're going to add a little more. Go back to 5. I'm going to take this to 70% off of the peak load. And we'll talk about some auxiliary cooling strategies to help make sure that everyone sleeps well at night. So now we're definitely shaved a lot of peak off this thing. 70% off the peak. We're down to 1,686 kBTU per hour as a peak from March through November. So this thing's going to bite quite a bit into the load off of the ground loop. And we're at about, looks like 36% of the total annual energy that's rejected to the ground loop has been reduced. So that's we're shaving off quite a bit. So let's see what our projections might be. Now at 5 years, we're at 86 degrees. So if we look at that, get that out of the way, chances are we're really never going to get over 85 degrees with this. But for those of you that are still convinced that heat creep does occur, here's a way that I would recommend approaching an auxiliary cooling device. I might look at a staged compressor or a staged cooling tower. So if you needed to, you could bring in more of that cooling capacity should that heat creep actually occur. You may never not need it, or you could leave the infrastructure in place to add more cooling device later. So that's one way of doing it. Of course, you could also start the auxiliary cooling in earlier, say at the end of February, or whenever the loop starts seeing, say, 75 or 80 degrees, you could start bring in auxiliary cooling. It's whatever fits the situation. So with that, we would probably have a safe operating system and resolve these issues of poor comfort, nuisance lockouts and whatnot. But let's take a look at some other ideas. If we have to go with the auxiliary cooling, that's going to get us back, get the system back to being reliable. But what else can we do? Well, we see a lot of times that outside air is a big issue on a commercial job, whether it's in the cooling or the heating mode. We've often find economizers on ERV equipment locked open 100% of the time, 24/7, doesn't matter what the outside air temperature is. And what we what a lot of us do, of course, is put in occupancy or CO2 sensors to only use that much outside air that's required to meet code. And then, of course, by code, if you get too hot or too cold in outside air temperature, you can shut your economizer down. But we find a lot of times ERV enthalpy wheel equipment is miscontrolled or it's malfunctioning. And when it's supposed to be using the energy recovery ventilation component, quite often they're getting too much outside air mixed in, and it's exceeding code, and it's just putting much more load on the ground loop than is necessary. Another suggestion would be, what can we do with that rejected heat? Is there a use we can put it to? Well, in a lot of these big retail facilities, they'll have a restaurant component, and it's amazing how much hot water they use for dishwashing and that sort of thing. So maybe by adding water-to-water heat pumps, you can also use that to scavenge heat and put it to good use, and it'll help in the load sharing. And you may look at a combination of the above. We've also been experimenting successfully, I might add, with putting in auxiliary horizontal ground loops, very shallow, and controlling them to run it, say at night, if the surface temperature is too hot during the day. And of course, you have to tailor the controls for this, but what we're finding is a lot of times we can shave heat off with a smaller auxiliary horizontal loop field, maybe even put it in a parking lot, in a parking garage, that sort of thing. It just depends if it's viable. You have to understand your climate, heat gain on whatever surface component. So there's a lot of things to consider, but it is something to keep in mind if the situation fits. Don't have a lot of other things. I'd like to open this up for questions. Anyone would like to discuss this and see what we can do.
Hi, Terry. Just a quick question.
Yeah.
Regarding control strategy, obviously in this scenario, let's say you've peaked 50% or 70%, would you, in your controls, obviously, I think you mentioned that it was a primary, secondary system.
Right.
So would you basically go to the ground with a VFD when the temperatures are mild and then ramp up your VFD up to, let's say, 90 degrees, and then once the loop or the entering water temperature from the loop gets to 90, then you kick in your auxiliary?
You could. It would be dependent on the building usage and whatever other variables involved. Quite often what we'll do on a decoupled ground loop, we'll pick a point depending on the efficiency of the heat pumps and the load profile. For, let's say, for sake of our argument, that we started injecting from the ground loop when the loop temperature on this example, say, hit 75 degrees, and we might have only been at 20% flow, because all we're trying to do is temper the loop at the least amount of water flow possible. And then as the loop continues to increase and we increase flow rate on the injection pump and we can't stay up with it, then I would be looking on this case of maybe bringing in first stage auxiliary cooling, say maybe at 80 or 85 degrees. What we probably would look at is the efficiency of the heat pumps, because different brands and all at different entering water temperatures have different EERs. So I think it would be a judgment call based on your product that's in the facility. In this case, I know the ClimateMaster TE30s, their EERs start dropping off pretty substantially above 90 degrees. It's, you know, the modern heat pumps, even at 90 and 95 degrees, have great EERs, but right. Compared to at 80 degrees, it's quite a difference. So I would probably be looking at starting at 80 or 85 degrees with the auxiliary cooling device. And if you had the capability with your controls to trim that and see how it performs, I think you could learn over a year. And I'm not a controls guy, but I'm told there are certain smart controls out there, so-called smart controls, where you can program the controls to say trip to an earlier staging point with your auxiliary cooling based on history.
Oh, okay.
So now again, I don't know if the controls guys are lying to me, but I'm told they can do that.
Right. Okay, thanks.
GLD is a pretty good tool for forensics. We, at any given time, with our company, our workload is anywhere from 25 to 50% forensics. And although most of the time it's not the size of the loop field as the issue, it's usually controls, outside air related, that kind of thing. We do run into these projects, vertical and horizontal, both on a commercial project, where GLD's been a pretty good asset to figure out what's going on. The biggest problem I find is getting the original load data, and sometimes even I've got one project right now where I have two different horizontal borehole configurations on a loop field that is definitely undersized, and I can't get anyone to confirm exactly which horizontal bore field configuration went in. So I'm having a little bit of fun with that one right now, and I'm still trying to figure out, if no one will tell me, how I can figure out what went in without eyewitnesses or getting a backhoe out there.
Terry, I have a question for you.
Yes, sir.
You know, you've used the hybrid sliding tool to look at how the loads are going to be split between the geothermal loop field and whatever auxiliary system is going to go in. Could you show us how you can export sort of the finalized loads profile and then look at it in Excel so we can actually see this output from GLD?
Yeah, and I'll be honest with everyone here. Dan's been teaching me how to use this feature. I've been doing things manually. Come to find out, GLD does this for me. I just wasn't using it correctly. So what we can do is we can go here under Export File under the File menu and export our hybrid monthly or hourly loads. For convenience, we're going to go to the monthly loads here, and that's going to save in your GLD subfile folder under Load Files, Hybrid Data Files, and it's got Hybrid Monthly 12/3. It's got the date on it. I've already got this titled as Big Job 1, so we're just going to resave. And then if I can find let's see, program files, and you can go back into your subfile directory. And which one is it? Monthly data, is it? Or load files? Here we go, hybrid data files. So what we have is a text file. And this is giving us information that we need to really convert into another format that we can see. And I thought we had that resolved, guys, but it's not as frequent as it was before. We have the data we're looking for, it's just not easily recognized. So yeah, what we're going to do is we converted it to an Excel file. And that's what our example is here. So we have, this is on a monthly format. These were our original peaks for cooling and This is our hybrid. See if I can get this shifted over. So we're not doing anything in this case for the heating, so everything's for the cooling. So we have, let's just highlight that guy, and that guy. So all we're looking at is our cooling loads, and this gives you a comparison. You can, if you're handy with Excel, you can graph this if you're having to work with a client or a cooling tower vendor, whatever, to show them what you're looking at and what you're trying to attain. And here's your total cooling loads. And then here's your hybrid total cooling loads, which can really be useful, especially if you're going to be doing an economic analysis of this thing. So it might help you on saying, okay, where do we select our first stage cooling stage on a cooling tower, if we're going to have a staged unit, which would make sense. And then, you know, when do we ramp up to more auxiliary cooling capacity? So this can help you in those decision-making processes. And GLD's been pretty handy for this. Like I say, up until recently, I've been doing these calculations by hand, and come to find out it's just a few mouse clicks away to, you know, with the help of GLD to do this. So another thing you can do is look at a summary of this in graphic format right on your modules. I'm going to take away the legend box here for a minute, and I'm going to, since we're not messing with heating, and delete heating, try and simplify this guy. So we have 4 representations here. Total cooling loads, peak cooling loads for the ground loop, and those are the ground loop, and then we have hybrid total and peak loads. So we're going to put the legend back in here, and I'm going to see if I can expand this a little bit. Oops. Hope everyone can see that a little better. Maybe I can even enlarge it a bit more. There we go. So what we have now, the heavy blue line is our ground loop total cooling loads annually. And you can see that's a pretty good chunk of heat rejection. The green, solid green line is our peaks, and that's what we shaved on this thing. By shaving those peaks, you'll also notice on the hybrid total cooling loads, which is I can't make out that color, guys, I'm sorry, but the hybrid total cooling loads, I believe, is this line right here. It's blue dashed. Okay, so that would be this line. Okay, and then here we go again. And then we have our hybrid peak cooling loads, which is this dashed green line. So all of a sudden, you can see in a visual representation what your auxiliary cooling device should be capable of handling here. And it's making a pretty big difference on this cooling load. And for whatever reason, the original load, who knows, maybe it was intern in the original engineer's office or whatever, doesn't matter. This is what we've had to deal with, and I'd say probably on the forensics jobs that we see, I'd say probably less than 20% are an undersized ground loop. Most of them are usually related to bad controls, not bad controls, but a bad sequence of operation. And we've even seen some cases where after 5 years, the system was shutting down, and then pulled out an air filter, and all it was caked dirt, and of course the ductwork was contaminated, and so was the DX coil. But we have found things that simple that could have been addressed without getting lawyers involved. But when you see something like a ground loop that's severely undersized, that can get pretty expensive, and to add in auxiliary cooling or heating can be an issue. But again, this graphing feature with GLD is pretty handy, because now you can share with the client and anyone associated with the project what the impacts are and what you're doing to resolve the issue. More questions? Dan, thanks for bringing that up. I meant to do that. That was a good prompt.
Terry, if nobody else has a question, I'll kind of ask another one that's kind of an extension. You mentioned that you see the controls being a problem. What's a thing to look for? Like, give us an example of a bad control sequence.
Oh, okay, great, good, very good question. Well, for example, we've seen several projects where heat pumps had a really short lifespan, which was a real big indicator that something was miscontrolled. And we just recently visited a project where it had a central plant, and they were banging the big water-to-water heat pumps. These were 30-ton units. And the sequence of operation overrode the protection measures of the heat pump control board. So when the water-to-water heat pumps were supposed to go from cooling to heating or heating to cooling, there's usually a delay cycle. The reversing valve will trip going to either direction. It'll give it a minute or two for the refrigerant within the circuits to equalize. Well, what they were doing, they were overriding this, and they were banging this thing from cooling to heating. And there's like, I don't know, I think there was 8 of these 30-ton water-to-water units, and they were just hitting them so hard. They were eating compressors, like they were rotating the heat pumps, but still they were probably going through these nominal 15-ton compressors, oh gosh, as many as 5 or 6 a year. And, of course, they had 2 15-ton compressors in each heat pump. So that was pretty expensive, plus there was a lot of downtime. The other thing we've seen on bad control sequences, it's usually related to outside air, where we had one school in Wyoming a couple of years ago. We'd actually done the loop design, and everyone's complaining the loop was running too cold. And sure enough, it was. It was running down the low 30-degree range. Some of the heat pumps were tripping out, but they shouldn't have been. As we found out later, some of the circuit setters were the wrong size on those things, so they were getting insufficient flow, but that wasn't the issue we were concerned about. Well, what we found was, and this is really common, I'd say well over 50% of the jobs we see is outside air being brought in through an economizer when it should be going through the ERV component. And so middle of February in central Wyoming, outside air temperatures of 0 and 5 below 0 and even colder, and they're bringing in cold outside air 24/7, and I was amazed the loop field was staying as warm as it was. But we've also seen heat pumps, residential type heat pumps with strip heaters in them, and where we've seen the control sequence for heating. We actually talked with one controls contractor on a school, and he said, well, heat pumps don't work in cold weather, so I made a change in the controls to bring in the auxiliary strip heat before the heat pump came on. I was shaking my head. So, and of course the customer was paying for that extra cost, and they were blaming us in the loop field, and we said, well, we're not trying to throw anyone under the bus, but the sequence of operation was this, and your controls guy that you wanted to use decided to make a change without considering the cause and effect. So I could probably bore you all day with control stories on ground source heat pump systems. There's a lot of them out there. I guess my biggest problem with a lot of controls guys, they'll put in a proprietary control system with closed architecture, essentially you're tying in the client in perpetuity to that controls contractor. And so whatever he does, it's black box and you may never know what he's doing. And I'm a real big advocate of having at least sufficiently open architecture that you can look at a BAS system remotely and look at set points in different zones, how heat pumps are operating, that sort of thing, because you can do a lot of forensics at your desktop before you get out there. And then a lot of times we'll see things that don't make sense where, and I'm sure you guys that have got experience with forensics will attest to this, where someone will say, well, the control screen is saying we're doing this with this valve or this pump, and then you have boots on the ground and you look at it and let's say a valve is supposed to be shut and it's open. The BAS system's wrong. So sometimes there's no substitute for putting boots on the ground and doing a point-by-point check on the control sequence of operation. And that's how we determine a lot of these issues for comfort and reliability. It's frequently something is not compatible with the operation of the heat pumps or the overall basis of design of the system.
Thanks, Terry.
You bet.
A question from Richard here.
Yes, sir.
When you loaded in that new energy file from Trace, can you explain again why, even though the total energy increased, your annual equivalent full load hours stayed the same as originally?
Because of the, let's see, the calculation for the full load hours is a proportionate value of the peak versus the total annual. So all it is like say it's a proportion. So,
okay.
So if I'm just
right.
reducing by 50%, then you're not going to change the full load hours.
Right. So our peak full load reduced correspondingly.
Yes, sir.
Yes. Yeah, got it. Okay. Second question to Dan, I guess. So I've seen the procedures for importing train trace files. What about carrier HAP monthly energy data files?
Since you asked me the question, I'll be happy to answer it. At present time, we've been unable to communicate effectively with the carrier corporation about their HAP tool, and everything can be done quite easily through an Excel intermediary. Okay. If you can get the data out of carrier HAP into a monthly loads format, you can copy from Excel and paste it in, or if you have an hourly profile, you just use the same format that comes basically by default inside of GLD in the loads folder. There's a sample hourly data file from Excel, like a CSV file. You just have to replicate that structure, and it's very, very simple. And then you can bring it in from carrier HAP or whatever, using that as an intermediary.
Okay,
Richard, I've got a actual a primer from Carrier on how to export the right data into a format that makes it easier to massage into GLD. Okay. And I would be more than happy to email that primer to you.
Okay, thank you.
Or anyone else that wants it.
Sure.
I've got a new email, and I'll just give it to you right now as soon as I can. We've got a new website coming up, and I just can't remember. Let's see. There it is. It's t.proffer@gomajornow.com. The old email will work as well, loopman@majorgeothermal.com. But and of course you can contact Jeff or Dan, and they can get my email address. In fact, I'll just forward this help file to Jeff and Dan, so they've got it and it's handy.
I'll post it on our website.
That'd be great. And I've got these examples of, some years ago I put, let's see, where is it? It's not what I was looking for, sorry. Here we go. I put together a summary sheet. I've got one that's also another tab that has where you can paste in the hourly loads, and it'll automatically give you a summary of the monthly loads, and it does the same thing that GLD is doing, but I've got these graphing features I put on where it overlays the cooling and heating, so you can get a sense. And in this case, I'm sorry, the scale of the graph is not right for how big these loads are, but it can be a useful tool in just kind of getting a perspective on your loads. For example, if all of a sudden you had a really huge cooling load in central Canada in January, and you know intuitively that shouldn't be there, and gives you an idea of what to look for. So I'll send some examples of these types of spreadsheets that you can dump data into, and you can actually copy and paste and export this data right into GLD. So they can be pretty handy. Oh, my screen blacked out, and I guess we need that driver's maybe not working as well as we thought, Jeff.
We're okay on this end.
Oh, okay, it's only blacking out on my end. That's okay, as long as you guys can see. Any other questions?
Richard again here. How common have you found this mythical, perfectly balanced system where the annual energy load for cooling is the same as heating? I do loops in Canada where it's always heating dominated, and I continually run into people that say, oh, you've got to adjust the building design so that you use more cooling load because you must have, this balance situation, which, certainly doesn't apply in the southern U.S. where it's cooling dominated, and will never apply in extreme climate of Canada where it's heating dominated. But I presume those are the loop installations that tend to be the most problematic.
Actually, what I'm finding is that's by definition, most commercial jobs are either going to be they're not going to be balanced. You're either going to be heating dominant or you're going to be cooling dominant. And everyone makes this big ado of balancing the loads to have this perfectly balanced loop field that you'll never have this theoretical heat creep or theoretical heat loss over the years. And a good way to test this, Richard, is pull out your cooling or your heating loads entirely and run your loop simulation. What you'll find is, if it's heating dominant and you pull out all the cooling load entirely and run it, you're going to find that in most cases the loop temperature on the first couple of years doesn't drop more than a couple degrees. And the reason is, whenever a ground loop is not being stressed by heat rejection or heat of absorption, and even when it is, the reason they work so well is because they're always trying to return to undisturbed temperature conditions. And everyone, and Dan and Jeff will probably cringe what I'm about to say, but I live in the Rockies. We've got like truck shops that are commercial in scale and scope, and they're heating dominant, 8, 9, 10,000 foot elevation, and we'll run those things heating only, radiant floors, all through the winter season. Loop never gets down to 35, 32 degrees, whatever we designed it for. And the next fall, when they start heating again, they start out at whatever the undisturbed temperature was, 48, 49, 50 degrees Fahrenheit, and yet you look at the GLD simulations, and it's not just GLD, it's a lot of other software. They're predicting that over time, that loop temperature should, whether it's 2 years or 20 years, that loop temperature should get down to catastrophically low temperatures that should not serve as heat pumps. But in reality, that doesn't occur. The reason being is that ground wants to force that loop to go back to undisturbed conditions. So whenever you've relieved the load on it, or it's a low load, that loop recovers very quickly. Good point to make on that. The ASHRAE specification for thermal conductivity testing says you're to allow a ground loop to rest for 5 days before you start data logging. Well, the purpose of that is to let any heat dissipate from the drilling process, changes in aquifer conditions as affected by drilling or that kind of thing. We do a lot of TC testing, and we will wait that 5 days, but we might go in on a lot of them. In fact, this was a big question, and so we started testing the loops after the drilling process in a variety of conditions. Dry conditions where the loop was, excuse me, air hammered, and a lot of mud rotary drilling. And what we have found is actually within 2 to 3 days, if not the first day, the loop was back to undisturbed conditions, that what we determined was undisturbed after we had allowed the loop to rest for 5 days. So what I'm saying is I think a lot of people get really wrapped up in this load balancing exercise, and yeah, that's a good thing if you can do it, but what if you're building, just because of the occupancy and the usage and how it's being used, there's no way you're going to change it. What if it's a retrofit? And like I say, it's not as big a deal as people make it out to be. And one way to test that is, like I say, if you're worried about heating side or the cooling side, pull out the opposite load and run your simulations. And what you're going to find is it doesn't bother the ground loop that much.
Thank you, Terry. That's very helpful. It certainly reinforces our experience. We designed the borehole thermal energy storage in Okotoks, Alberta, for the subdivision of houses that's heated from heat that we collect in the summer and store away in a borehole field for the winter, and it's probably the biggest of its type around, and you've got to do absolutely everything possible to insulate that borehole field from the rest of the world, and we recover only 50% of the solar energy that we pack in there in the summer to get it out in the winter. So
absolutely,
Earth is not a good storage medium. It conducts
I was just going to say that.
Yeah. One last question on thermal conductivity testing. What do you recommend for horizontal boreholes? We've been drilling in some horizontal loops at directional boring at 12 and 18-foot depths. And do you have recommendations for thermal conductivity testing practices there? For horizontal borehole?
For a horizontal borehole, I run them the same way I do a vertical, to the same specifications. In a lot of times too, you might keep this in mind, Richard. We'll do a lot of point testing with a handheld like Decacon meter, where we'll excavate to pre-designed depth, and we will use that handheld meter. And we actually did our own independent testing ourselves on a couple of projects in Wyoming for the Air Force, where we did a horizontal bore, we did a trench ground loop just to lay it in, just like you, and to replicate the horizontal bore, only it was a trenched loop, backfilled it, and then we did an excavated pit loop, and they used a Decacon KD2 meter, I believe it is, and there may be other products out there that do the same thing. And our thermal conductivity values based on the average TC test for the horizontal bore and trenched loop, and the point TC testing using the handheld meter, they were within 5% of each other. So we were pretty impressed with that, and we've repeated that test on other jobs. And so if cost is an issue and time is an issue on a horizontal ground loop, you might want to consider a handheld TC test meter.
Okay.
The other thing I like about that, it gives you an actual measured diffusivity instead of an estimated or theoretical diffusivity as per an average TC test.
Thank you.
Yes, sir. Well, if there's no other questions, I guess we'll wrap it up, guys. Any last comments?
Yeah, thanks, Terry. We'll post the recording here so that people have the opportunity to go back and take a look again if they missed something.
Okay. Well, it's been my pleasure. I appreciate it, and I'll send those.
Thank you, Terry.
I'll send the help file and the examples of the what I call my reality check spreadsheets for dumping hourly load data into.
Okay, terrific. Thanks again,
right.
Terry, and thanks everyone.
Thank you very much, Terry. Very helpful.
Thank you, guys. Bye-bye.